All right, we're going to define electric potential difference. It's also known as voltage. This is one of those really poorly named quantities in physics. There's a lot of different names for it. You hear it called electric potential. Sometimes you hear it called electric potential difference. Sometimes you hear it called electromotive force, which is the worst name. And then you'll often hear it called voltage difference or change in voltage, and they all mean the same thing. Why is it so screwed up vocabulary-wise? Because these ideas were developed over a long period of time by people who didn't really know what the heck was going on, and so we just kind of kept this collection of names for kind of the same thing. Usually it's like an EMF for a battery, so we're not going to deal with batteries right now. Well, let's review a little bit. Let's review what an electric field is. If I have space, just some empty space, and I put a charge in this space, and it's always going to be a positive test charge when we define the electric field. If there is a force on it, due to the charge on that object, then we are in an electric field. In other words, something has happened to this space where if you place a charged object in that space, it will feel a net force or an electric force. Now, if I place this object in this space and it had no net charge on it, it would feel no force. You have to have some charge, a net charge, to feel a force. And that's what we mean by an electric force field. It's a region of space that because an object has some charge, it will feel a force. And so we define the electric field as being that electric force divided by the charge on the object that's in the field. Now, one of the things that's important to understand is that what causes the field, why there's an electric field in that space, is because we have separated charge somehow. All right? But that separated charge is not the same as the charge on our test charge. Now, this test charge does create its own field, but it doesn't feel its own field. Other charges would, but it doesn't. So the source of the electric field is not this test charge. Sometimes we call the test charge Q naught, so I'll put a little there. Now, if I move this thing around, I can say, well, if I put the charge here, it would feel a force like this, so I can connect it all with an electric field line. And let's say we're in a nice uniform electric field. Now, these lines of force, Michael Faraday thought they were really there. You know, he thought he visualized that, hey, there must be these little tubes or lines of force. We now know that those electric fields are not there. We have field theory, which was developed by James Clerk Maxwell and so on. But they're really still, it's a really handy thing to think about. The electric field is a way of visualizing the space around there. Now, the way we got this is that over here, there had to be some positive charge separated from some negative charge. Like that. So somewhere out in the universe, there's separated charge, creates this electric field. I place my test charge in there. It feels a force. The amount of force it feels per unit charge on the test charge, that's the strength of the electric field. The direction of the electric field is the direction it pushes on a positive charge. And so if I stick an electron in there, what direction is it going to get pushed? Well, these lines are to the right, so a negatively charged test charge would be pushed to the left. Okay, any questions so far? All right. Now, but we're dealing with forces, and if I move, now I want you to think about this. Okay, wake up, look at me in the eyes. Look me in the eye. Okay, those of you watching online, you can't look me in the eyes. Well, let's see. But off screen. All right, that's horrifying. we have a force here, and if we move that object, that force through a distance, what do we call a force through a distance? No. What do we call a force through a distance? Do not give me word salad. Think. Force times distance equals work. So imagine I have a field like this. So here's my electric field. Now I'm going to put a test charge right here, and I'm going to, some outside agent, me, right? Okay, so this, we've got an electric force like this, but I'm going to apply a force to it. And this is me, and I'm going to barely exceed the electric force so that I actually, and I'm going to push this guy from here, watch, it's really exciting, to over here. All right? So here's my displacement. So I did work on it. I put energy into it. So that means that by virtue of being here in the electric field, if I let go of it, what's it going to do? Bing! It's going to go. And all that work that I put into it by doing work against the electric field is now stored up in that electric field due to the position of that test charge. If I release the test charge, the field will do work on the charged particle and increase its kinetic energy. It's good. So when I push it against here, I gain electric potential energy, joules. Now we did this with gravity fields. Actually, let me change this picture. Gravity's a really good analogy. So let's see gravity. Here's the ground, the earth, and it's pulling down on everything. So I'm going to draw gravity field lines. So when I lift something up, here's an object that has a certain amount of mass. And I'm going to lift it up a certain height. So what have I given it? I've given it gravitational potential energy, right? And we said that that was the force I had to overcome. It's just the weight of the object through a certain height. And that was gravitational potential energy. Now I can do the same thing with an electric field. So let me call this a gravity field. Get you used to the idea of thinking about fields. Well, I don't have a planetary surface. Maybe this is some chunk of metal with some charge on it. And we're going to have electric field lines. And suppose I have a little object right here. Now, if I lift it up here, maybe I've changed this gravitational potential energy, but here's what we're going to do. We're going to pretend like we're not in a gravity field. We're only in an electric field. So I'm going to lift this thing up. It takes work to do that. What's the force that I have to apply? Q times E. That's the force. And then I'm going to call it some delta. What do they use in the book? We'll just say some distance. They use D. I'll just call it some distance D. I'm going to go from here up to here. And so now I've done work, and I'm storing that work up, E times D. I've stored that in, and we're going to call this U sub E. Now this time the E, you know what? I'll make it a capital E. I don't like the variables the book uses, so I'm going to put a capital E for electric. So this U sub E is equal to the, well, this is electric potential energy. So that electric potential energy is equal to QE times D. So Q here is the charge on my object. E is the strength of this electric field, and D is the distance through here. Now, and so this is how much electric energy, how much energy is stored up because this positively charged object is at this location in the electric field. Now we're going to do something, we didn't do this in gravity fields. We didn't do this for gravity. We're going to do it for electricity though. We're going to take this and we're going to divide it by the charge on my charged object here. So this charge cancels. And I get this quantity right here. This is energy per unit charge, which is a joule. That's the metric unit of energy. And what's the metric unit for charge? Coulomb. What's a joule per coulomb? Anybody know? It's a volt. You've heard of volts, right? You have a battery, and it's like a 12-volt battery. What does that 12 volts mean? That means that battery will deliver 12 joules of energy for every coulomb of charge that comes out of it. Okay? And so a joule per coulomb, by definition, is called a volt. And it's a B. Now, let's take a look at what, so I can say this. I can say V equals E times D. And now we're dealing with a lot of quantities here that are kind of new. So maybe I can, in a few minutes, I'll summarize this with a quantity chart. But this is where it's really, electricity, it's really important to make a good quantity chart, because when you're studying and reviewing, it's really easy to forget what all these units are and what the variables mean and what they're called. So, now, by the way, when you get to higher level physics, like upper division, junior, senior level physics, when you take a advanced classical mechanics class, you will take this and you'll divide it by mass. And you'll have joules per kilogram, and we call that gravitational potential. Okay, so this right here, voltage, is also called electric potential. And they leave the energy off. It's a really stupid way of naming this, and I'm sorry, but you're going to see it. Sometimes they just call it potential or electric potential, or sometimes they call it voltage. I usually use voltage. Sometimes, potential, electric potential. If I say electric potential energy, I'm talking about joules. If I say electric potential, and that's it, I'm talking about joules per coulomb. So get used to, you'll get some practice. One thing you can notice is that if, let's say I've got an electric field like this. Here's E. And I put my positive test charge here. What's the direction of the force? This way? if I release it, notice that I'm losing electric potential energy. Just as if I take a rock up here and if I take this and I drop it, it loses gravitational potential energy. But what does it become? Kinetic energy. Same thing's going to happen here. I'm going to release that, and then it will lose potential. So just like in gravitational potential, we often pick like this. We're going to call this 0 volts. And as it falls, as this thing moves, like maybe this is 12 volts. Okay? Now, so I can say that the change in voltage from here over to here is negative 12 volts, isn't it? If I end at 0, but I started at 12, that's a voltage drop. I lost voltage. What did I gain? Well, I probably gained some kinetic energy. So there's a conservation going on there. Now, I'm going to do this. The change in voltage is equal to the change in electric potential energy per unit charge. So, but this is also equal to the electric field times the distance we go across. Now, remember when we did work? What if I started here, but my object ended up over here? What we say work was? Work, this is a little bit messy. We said that work, what was the equation for work? Work equals force times displacement times the cosine of the angle between them, or the dot product. Some of you have done dot products in your math classes already, or scalar product. Don't worry about that. It's just the force times the distance times the cosine of the angle. See, if I go like this, I would say, well, the change in voltage from here to here is a result of the electric field. It's really the electric field times the distance times the cosine of the angle. So if this is my distance d from here to here, and this is theta, only the component of the distance that's parallel to the electric field, does that contribute to any change in voltage? So if the electric field is doing the work, we're losing voltage. But we're, and that energy per unit charge is going somewhere. It's becoming kinetic energy. Or if we send it through a circuit, it's going to be doing some work for us, creating light or heating up a toaster or making your cell phone run or something like that. We're going to get to that next week when we talk about current and so on. So really this is very similar to what we talked about before. And since this from here to here, this is a loss. I should have put a negative in it. It's a loss of potential energy. Delta E is going to be negative. So what I can do is I can say this. The electric field can also be equal. Let's assume everything is parallel. I don't need to worry about cosine theta. It's equal to the change in voltage divided by the distance, but it's going to be, you need a negative in there. Is anybody in here in Math 6 by chance? That's pretty advanced. Some of you might take it. This is related to a thing called a gradient, when you take the derivative of a scalar function and you get a vector out of it. That's a little advanced right now, but it's in your future somewhere. So let's work a, yeah. So if I've got a plate of, let's work a little example. If I've got a plate of metal like this, and another plate of metal like this, and let's say I take that plate of metal and I hook it up to a 12-volt battery. I think the robotics team uses a 12-volt battery. Yeah. So we'll hook it up there, and then maybe this will be on the positive terminal, and then we'll hook this up to the negative terminal. And what the positive terminal does is it pushes, actually it pulls in electrons, leaving a net positive charge on this plate, and a net negative charge on this plate of metal. And what that does is that creates an electric field from here to here. Okay, and only got a few minutes left, but I really want you to focus on this. This is going to be a really important idea when we get to circuits. Well, this kind of is a circuit. But let's say that everything right here is at 0 volts. That's our floor. So what a battery does is it boosts up the voltage. So you go through the battery and you go, oh, everything over here is at 12 volts. And that's going to push charge over here, and then put negative charge over here, the same amount, and then I'm back to 0 again. I'm just going to go around in circles. So I'm going to jump up to it. So guess what? From here to here, what do I have to do? I'm falling down the electric field. If I put a little positive test charge right here, and I fall down the electric field, it's like holding this eraser and letting it fall down a gravity field. It's losing potential. So this change in voltage from here to here is equal to negative E, the electric field, times D. Now you got to be really careful when you're doing these equations, because we have capital E for mechanical energy, and now we're using capital E to represent electric field. Sorry. So, here's what this lets you do. You can figure out what the electric field is between those plates. D is the distance between the plates. By the way, this little arrangement of two plates with charge on it, it's called a capacitor. And it's an electrical device. That's a little bit beyond where this class is going to go. But take AP Physics C next year, or calculus-based physics in college, and you'll get to capacitors. So every electronic device you have has, your phones, computers, everything has capacitors in them. It's a way of storing up energy by creating an electric field. And then it's complicated, but it can use that energy to do different things. So I can say, well, let's see, given, I can say, hey, the voltage is equal to 12 volts, and the distance is equal to 2 millimeters, and then I can say, find, well, what's the strength of the electric field in there? Well, it's pretty easy. The strength of the electric field, I'll just rewrite this equation. Delta V equals negative E times D. And the electric field, E, is equal to negative delta V over D. And the direction of the electric field you have to get by inspection. Just look at the problem, look where the positive charge is, look where the negative charge is. The direction of the electric field goes from positive to negative. But for the magnitude of it, 12 volts divided by 2 millimeters. But what is 2 millimeters? Right, you divide that by 1,000. It's moving the decimal to the left 3 times. So what is 12 divided by 0.002? I think it's 6,000. 6,000. What units? Nope. Look at, you're making it harder. Volts per meter. And we said, wait a minute. We thought electric field was newtons per coulomb. That's what we did last time. Well, let's 6,000. What's a volt? A volt is a joule per coulomb. Now we got to put this meter in there. So it's coulombs times meters divided into joules. But what's a joule? A joule is a newton times a meter. The meters cancels out. We get newtons per coulomb. So a volt per meter is dimensionally identical to a newton per coulomb. So here's the bottom line. If you have an electric field, you can store energy in that electric field by forcing a charge. Like if here's my electric field, and I take a little positive test charge and I move it against the electric field, some outside agent has to force that to happen. So I got to transfer energy from that outside agent into the electron, or into the positive charge, and move it across that negative charge. So I'm gaining energy, and then I divide that energy by the charge on my test charge, so I'm gaining voltage. Now last thing. Okay. So here's something that's kind of interesting. Look right here. There is a surface right here in between, in our imagination, an imaginary surface area, where everywhere on there, I've moved the charge the same distance through that field. From here to here, here to here, here to here, from here to here. So therefore, the voltage is the same. On that surface. We call that an equipotential surface. So an equipotential surface is like, maybe this is at 12 volts and this is at 0 volts. So if it's right directly between them, what is it at? 6 volts, that equipotential surface. So no matter where I am on this imaginary surface, my test charge has a voltage of 6 volts. And so if I take my little test charge and I move it around here, I'm not changing the voltage at all. It takes I'm not doing any work for or against the electric field, so I'm not changing the voltage. And so you might see a cross section, like on an AP test. I've seen this. You have something like this. We're going to draw this in cross section now. This is like 12 volts, 0 volts, and then you'll have lines like this. And these are the cross sections of the equipotential surfaces. This is 12, 10, 8, 6, 4, 2, 0 volts. And it's not that big a deal, but okay. So well, I think we're running out of time, so I think we're just going to stop there. So here's the bottom line. We're storing energy in electric fields because I'm moving a charge through that field. If I work against the field, I'm gaining potential, electric potential. But if I go with the field, if I move that positive test charge with the field, I'm losing potential. It's just like if I lift this calculator against the gravity field, I've gained gravitational potential. If I lower it down, I've lost gravitational potential. Okay. And potential is measured in volts, which is joules per coulomb. That is